Hello everyone, my name is Tim Harrigan. Today I will present Module 2 of the Appropriate Scale Mechanization Smallholder Farmers online course on the fundamentals of soil. First, I want to comment on soils as they affect mechanization and management. Then we will get into the overall course objectives and detailed discussion. Topography, or variations in elevation in the landscape, is a crucial soil characteristic of a soil management plan. The level ground may be poorly drained, and infiltration may be too slow for cropping many crops. Sloping lands are subject to water erosion, and soil conservation efforts will be essential for sustainable land use. Fine textured soils contain enough clay to make them sticky and slow to drain. They can only be worked when the soil moisture is just right, or the result is a cloddy surface and a poor seedbed. Coarse textured soils are easier to work with. Sandy soils drain quickly, so the timing of tillage and planting is not as important as with clay soils. Soil texture is a factor in selecting a cropping system. Some crops adapt to slow drainage and poor aeration, while others need loose, friable soils and irrigation for good yields. Coarse textured soils have a low moisture holding capacity, and drought often limits production more than finer textured soils. Soil texture often determines tillage options. Clay soils should not be worked when wet, but they resist wind erosion. Sandy soils are prone to blowing and benefit from cover crops and conservation practices to prevent wind erosion. Soil organic matter is a key component of soil quality and soil health. Plants grow readily in moist soils, and because soil aeration is poor in wet areas, decomposition is slow, and organic matter accumulation is greater than in dry soils. Frequently tilled, well-aerated upland soils often have conditions conducive to excessive soil microbial activity and oxidation that burns up soil carbon and depletes organic matter. It isn't easy to increase or even maintain natural soil organic matter levels in such soils. Mechanization can ease the burden of managing cropping systems profitably. Understanding soils is essential in selecting suitable crops and sustaining soil quality and health. The learning objectives for Module 2 are to understand some of the key aspects of soil and factors influencing crop growth, including soil development, soil quality and health, soil texture, soil physical properties such as bulk density and soil porosity, field capacity, moisture retention, soil color, organic matter and humus, and methods of soil conservation. Worldwide, soils are grouped or classified into 12 orders based on the level of development and the characteristics of soil layers below the surface. Each order has several suborders, groups, families, and series. This figure also shows the general climatic and vegetative conditions affecting the formation of each order. Soils are organized according to their qualities, such as mineral content, how they were formed, and key physical characteristics. Soils form from the weathering of the parent material, which is the basis of the mineral and organic matter that forms the soil profile's upper regions. Glaciers have a key role in soil development in the northern latitudes, and many soils are volcanic in origin. Climate and vegetation are key aspects of soil formation, as is topography, where the soil is eroded from slopes and deposited in low-lying areas. A soil horizon is a distinct layer of soil typical of the soil forming process. Horizons develop as the parent material breaks down over time from weathering. The top, organic matter rich A horizon, forms from decayed organic matter, often forest or grassland vegetation. The B horizon eventually develops, which is more blocky in structure as minerals are leached from the surface and influenced by biological activity. Soil groups in soil taxonomy contain soils with the same horizons and similar moisture and temperature histories. These are the major soil groups in Africa. This map groups regions based on the soil suitability for maize production. Some of the best areas for maize production are in East Africa. More detailed information for specific areas can be found in the Soil Atlas of Africa and other sources. You will often hear two terms used when discussing soil. One is soil quality. Soil quality refers to soil properties that influence the ability of the soil to carry out ecological functions and provide ecosystem services. Ecosystem services benefit humans by providing clean air and water, maintaining soil resources, and so on. Environmental factors affect soil quality. Management practices alter soil properties and affect qualities such as aggregate stability, water infiltration, nitrogen mineralization, and the biodiversity of soil organisms. Soil health and soil quality are often used interchangeably. Still, soil health refers to soil functioning in a holistic or ecosystem context and is difficult to quantify with single parameter measurements. Soil health implies soil biological integrity. Soil health refers to a balance among soil organisms, resilience to rebound from environmental stresses, and an ability to carry out ecosystem services. Now, let's discuss soil physical properties such as texture, bulk density, porosity, and so on. Soil consists of solids, liquids, and gases. An ideal mineral soil is 45% solid particles, 5% organic matter, 25% water, and 25% air. In most soils, the solids are mineral particles from the weathering of the parent material, such as quartz. Pore spaces exist between the solid mineral particles. The pore spaces are filled with water and air. Biological activities, such as root respiration and decaying organic matter, consume oxygen and create carbon dioxide. There is a continuous exchange of oxygen from the atmosphere and carbon dioxide from the soil into the atmosphere. Water entering the soil displaces air, and water is removed by drainage, evaporation, or plant growth, so that the pore space is once again filled with air. Soil texture has important management implications. The soil textural triangle shows the limit of sand, silt, and clay in 12 texture classes. Soils in the same textural class are similar. Each triangle corner is dominated by sand, silt, or clay. The largest class is clay because clay has the greatest effect on soil properties. Texture classes have properties important to their management. Texture governs how water infiltrates and percolates or drains through soil. Water moves through coarse, sandy soils after heavy rain. allowing farmers to enter the field sooner. But coarse soils have less water holding capacity and need more frequent irrigation. Soil texture impacts how easily soils can be worked, power requirements for tillage, and retention of organic matter and crop nutrients. In this example, you have a soil sample of 30% sand, 35% silt, and 35% clay. Start by entering the clay axis on the left-hand side of the triangle where the clay content equals 35%, and draw a line horizontally. Next, enter the silt axis at the 35% mark on the right-hand side and draw a line diagonally down to the left. Finally, enter the sand axis on the bottom 30% point and draw a line diagonally up and to the left. The intersection of these lines indicates that the soil texture is a clay loam. The relative fractions of sand, silt, and clay can be estimated differently. The simplest test is the ribbon or feel test, whereby you moisten a small sample of soil, squeeze a ribbon between the thumb and forefinger, and note how long a ribbon can be formed without breaking. If no ribbon forms, it is loamy sand. Ribbons 2.5 to 5 centimeters in length indicate sandy clay loam, silty clay loam, or clay loam. Ribbons greater than 5 centimeters indicate sandy clay, silty clay, or clay. Sedimentation methods are based on the differential settling rate of sand, silt, and clay. Sand particles settle more rapidly than silt or clay, and silt settles more rapidly than clay. Sand and silt particles will settle within a couple of hours. The fine clay particles may take several hours or even days to settle. The height of each particle layer relative to the total height of the particle column gives the percent sand, silt, and clay. In this figure, just by inspection, the sand measures 5 centimeters. The silt is 2.5 centimeters, and the clay is 2.5 centimeters for a column height of 10 centimeters. So, the sand is 50% mineral particles, 25% silt, and 25% clay. Referring to the soil textural triangle, the soil class is a sandy clay loam. If the soil had no pore space, it would weigh the same as the solid particles, the same as solid rock. Particle density varies according to the type of minerals in the parent material, but not by much. So the standard or common value in soil calculations is 2.65 grams per cubic centimeter. High amounts of organic matter can reduce that because organic matter is much lighter than mineral matter. The bulk density of soil is less than the particle density because the soil has pore spaces. Pore space is important for root and plant growth, so it is an indicator of soil quality. Measuring bulk density requires collecting a known volume of soil from the field and drying it in an oven at 105 degrees centigrade until it reaches a constant weight. This is known as oven-dry soil. Bulk density is then the weight of the soil in grams divided by the sample volume in cubic centimeters. Higher bulk densities indicate more soil particles and less pore space. Soil porosity is the volume of soil that holds air and water. A soil that is 50% porosity is 1/2 mineral material and 1/2 pore space. Pore space can be calculated from bulk density and particle density. If there were no pore space, bulk density is the same as particle density, and the ratio of bulk density to particle density is 1. More pore space results in a lower bulk density and a bulk density to particle density ratio of less than 1. As we saw earlier, the bulk density to particle density ratio is the percentage of soil that is mineral soil matter. So, subtracting that percentage from 100% gives the percentage of pore space. For example, if the bulk density is determined to be 1.3 grams per cubic centimeter, we can assume that the particle density is 2.65 grams per cubic centimeter. 1.3 divided by 2.65 is 0.5. We can multiply by 100 to express it as a percent. So the porosity equals 100% minus 50% equals 50% porosity. Soil compaction is the loss of pore space in the soil. Some soils are naturally compact, but crop management practices such as excessive traffic, annual plowing at the same depth, and intensive tillage can create soil compaction. Soil compaction inhibits root growth and slows water infiltration and crop growth. When root growth is restricted, crop nutrients and water uptake are reduced and crop yields decline. The cone penetrometer is one way to locate restrictive or compacted soil layers in crop ground. You press it into the ground with steady pressure and read the depth and degree of resistance. Increasing resistance indicates a greater level of compaction. Permeability is the ease with which water, air, and roots penetrate the soil. In permeable soil, water infiltrates quickly, roots are well supplied with oxygen, and roots easily explore the soil in the root zone. The number of soil pores, size of the pores, and continuity of the pores affects the rate of water movement. Large pores are the most effective in the movement and exchange of water and air. Coarse sand typically has large, continuous pores and high permeability. Clay soil has very small pores and very low permeability. A soil aggregate is a mass of fine soil particles glued together by clay, organic matter, and microbial and root exudates. Aggregates that occur naturally are called PEDs. Clumps of soil resulting from tillage are called clods. Soil aggregation improves permeability and promotes root growth, soil aeration, and water infiltration. The carbon within the aggregates is protected from rapid decay, so it preserves soil organic matter. Soil aggregates resist wind and water erosion. Soil aggregation is a sign of soil quality and soil health. People who design or use irrigation systems need to be able to measure the amount of water in the soil and describe the amount in the soil. Gravimetric methods directly measure soil water by weight. Collect, weigh, and oven dry the soil sample. The difference between the moist and the oven dry samples is the water content. Divide the water content by the oven dry weight and multiply by 100 to convert to a percent. Sometimes it is useful to calculate water content on a volume basis. The easiest way is to use soil and water densities if the bulk density is known. The volumetric water content is the gravimetric water content multiplied by the bulk density of the soil. In this example, the gravimetric water content is 22.4%, and the bulk density is 1.4 grams per cubic centimeter. The water content on a volume basis is 33.9%. Irrigation water is measured in inches of water, and it is easy to visualize the amount in the soil when expressed as inches. One can easily calculate the inches of water in the soil by multiplying 12 inches per foot times the volumetric water content. In this example, the water content on a soil depth basis is 4.4 inches per foot. When the soil pores are filled with water, the soil is at saturation. Gravity drains excess water through the soil profile, allowing air to refill the pore space. When drainage stops, the soil is at field capacity. Large soil pores are air-filled, and smaller pores remain water-filled. Field capacity is the ability of soil to hold water against the force of gravity. In well-drained soils, field capacity often occurs 2 to 3 days after a saturating rain when gravitational water has drained from the soil profile. Plants and evaporation from the soil surface then remove available plant water. At the permanent wilting point, soil water is held so tightly by the small soil particles that roots cannot extract it, and it is unavailable for plant use, and the plant will die unless it receives water. The graph shows the water holding capacity in inches of water per foot of soil depth on the vertical axis and soils of varying textures from coarse sand to fine clay on the horizontal axis. Following a saturating rain, most of the water in the sandy soils drains to field capacity under gravity, so little water is available for plant use between field capacity and the wilting point. Clay soils lose less gravitational water and have a larger amount available for plant use. Water is tightly bound by the small pores in the clay soils, and plant roots cannot extract water from the smallest pores, so a large portion of the water is unavailable. This table compares soil physical properties across soil textural classes from sandy on the top left column to clay on the bottom left column. Notice that in going from coarse sands to fine clays, bulk density decreases, total pore space increases, volumetric water at field capacity increases, the wilting point and available water by volume increase, and air capacity at field capacity decreases. Organic matter, aeration, and drainage are soil properties of interest to farmers related to color. The red color of many tropical soils is from iron oxide materials. Dark colors indicate decayed organic matter. Poorly drained soils often have more organic matter in the surface layers. Mottling and graying are associated with poor drainage or a high water table. Soil organic matter is an indicator of soil quality and a key component of soil health. Organic matter is material from plants and animals that decays to form humus. Humus is a dark-colored and decay-resistant residue from organic matter decomposition. Soil organic matter and humus are crucial for soil aggregate formation and stability, a major source of plant nutrients, and a key source of nutrients for soil microbes and biological activity. It is essential for soil water retention and drought resistance and a crucial aspect of soil resilience. New organic matter feeds soil microbes and releases crop nutrients quickly. Annual additions of organic matter are needed to increase or even maintain soil organic matter. Failing to add new organic matter or intensive tillage, such as with a moldboard plow or disc harrow, can also reduce soil organic matter quickly. Plowing loosens the soil and buries crop residues. The injection of excess oxygen accelerates the oxidation of the humus. Close contact between crop residues, soil microorganisms, moisture, and oxygen stimulates rapid decay that consumes new organic matter quickly. Conservation tillage, especially no-till, concentrates organic matter in the top few centimeters of the soil. This improves moisture infiltration, reduces crusting and erosion, and makes nutrients available where the roots are most numerous. Crop residues act as mulch and build soil organic matter. While crop residue may be harvested for feed, animal bedding, or fuel, and burning crop residue may simplify some cropping practices, the result is a loss of organic matter in the soil. Green manures, cover crops, livestock manure, and compost are examples of organic inputs that can be added to replace crop residues and soil organic matter lost in the cropping system. Mulches, such as straw, add organic matter, suppress weeds, retain soil moisture, reduce evaporation, and reduce erosion. Continuous row cropping causes the greatest decline in soil organic matter. Small grains are less harmful, while pasture or hay crops may actually increase organic matter levels. Soil conservation is protecting the soil from wind and water erosion. Erosion removes topsoil, which is the most productive soil for crop growth. Erosion removes the nutrient and organic matter-rich soil. Water holding capacity is reduced by erosion. Soil particles removed from the field obstruct waterways, and wind erosion degrades air quality. This photograph shows a severely eroded field in Oklahoma in the USA in the 1930s, before conservation practices were implemented. From a management perspective, the essential goals of soil conservation are to 1. Create conditions for rapid water infiltration. 2. When runoff does occur, reduce the volume and speed of overland flow to reduce sediment transport. And 3. Cover the soil with protective crop residues or vegetative cover to keep the soil in place. The photos on the left show changes in the landscape before and after multiple soil and water conservation measures were implemented. The measures resulted in reductions of more than 70% of runoff and 90% of sediment loss, resulting in soil stabilization, the restoration of vegetative cover, and a greater volume of biomass produced. Soil and stone bunds are barriers built along the contour to reduce runoff and erosion. The bund forms a barrier to water flow, spreading the water over a wider area for infiltration and slowing water flow, thereby dropping out soil particles and nutrient-rich organic matter. A terrace is a series of low ridges and shallow channels running across a slope or on the contour to capture water and control erosion. A demi-lune is a catchment to trap and conserve water. They are augmented with compost, manure, and organic inputs to build soil fertility for crop growth. No-till and low-disturbance tillage disturb narrow bands of soil for a seedbed. Crop residues form a mulch or protective soil cover. The residue protects the soil from raindrop impact, slows water movement to improve infiltration, and conserves moisture for crop use by reducing surface evaporation. In Burkina Faso, we worked with local farmers to transition from the moldboard to an inline ripper. The ripper tilled a narrow band of soil rather than tilling the field's full width. Reducing tillage intensity improves soil health, reduces the implement draft by 1/2 compared to the moldboard plow, conserved surface residue, and reduces the time needed to prepare for planting. In summary, soils reflect the environmental conditions of their development, such as climate, vegetation, topography, and underlying parent material. The top organic matter-rich A horizon forms from decayed organic matter, often forest or grassland vegetation. Management affects soil quality parameters such as aggregate stability, infiltration, nitrogen mineralization, and biodiversity of soil organisms. Soil health describes soil functioning in a holistic or ecosystem context, including the soil's biological integrity. Ideal mineral soil is 45% mineral material, 5% organic matter, 25% air, and 25% water. Total pore space is the volume that holds air and water. Soil compaction is the loss of pore space with an increase in the volume of mineral material, raising bulk density. Permeability, measured as hydraulic conductivity, is the ease with which air, water, and roots penetrate the soil. A soil aggregate is a mass of fine soil particles glued together by clay, organic matter, and microbial and root exudates. Aggregates that occur naturally are called PEDs. When the soil pores are filled with water, the soil is at saturation. Gravity drains excess water through the soil profile. When drainage stops, the soil is at field capacity. Loams and clay loams have greater plant available water holding capacity than sandy or clay soils. Organic matter is material of plant and animal origin that decays in the soil to form humus. Humus is the dark-colored and decay-resistant residue of organic matter decomposition. Soil conservation is protecting the soil from wind and water erosion. Erosion removes topsoil, which is the nutrient and organic matter-rich soil most favorable for crop growth.